Let's take a look at a one-to-one inverse function refresher. A one-to-one function is a function in which each output value corresponds to exactly one input value. So remember that the definition just for a function, right, we would say is a relation in which each input corresponds to one output value. So notice that we need to preserve this definition because this is just the definition of a function. And so we say a one-to-one function is a function. So I need each input to only go to one output. And now I'm adding this new thing where each output value corresponds to only one input value. So when I look at this example, it says determine if the following function is one-to-one. So you might recall from a previous class that in order to test if a function is one-to-one, we can think about this definition. It actually means that a horizontal line can only cross the function at most one time. And I can see that that is happening here. So everything is looking good here. So this is definitely, yes, this function is one-to-one. Yes, this function is one-to-one. Excellent. A one-to-one function has an inverse function. So think of, like, here are my happy little group of functions, like all the functions in the whole world. And then these ones are the ones that are one-to-one. So these lucky functions that are one-to-one, this group has inverse functions. So let's say I want to determine the inverse function of this equation, f of x equals 0.25x minus 2. So the one I was just looking at its graph, and now let's say I want to determine the equation of the inverse function. So I know that this function is one-to-one, so I feel good about this. So what I'm going to do is first rewrite f of x as just y. So I'm just replacing that, and then writing y equals 0.25x minus 2. So here, the way I've written it, y is just still equal to f of x. I've just replaced it to make the arithmetic a little simpler. Now I'm going to, wherever I see a y, replace it with an x, and wherever I see an x, I'm going to replace it with a y. So this gives me x equals 0.25y minus 2. And here, because I made that switch, now y represents f inverse of x. So now I'm going to solve for y in order to get f inverse of x. Okay, so the first thing I'm going to do is add 2 to both sides. So I get x plus 2 is 0.25y. And 0.25 is the reciprocal of 4, so I'm going to multiply both sides by 4 and get 4x plus 8 equals y. And because I just said that y is equal to f inverse of x, I'm given then, or what I've found is f inverse of x is 4x plus 8. And I can actually go up here and graph that equation on the graph of f of x equals 0.25x minus 2. So I can graph the inverses together and kind of see what their visual relationship is. Let's see, my y-intercept is 8. That's a little high to show up on the graph, but I can just start by plotting some points. So if I plug in negative 2, I get out 0. And if I plug in negative 3, I get out negative 4. So I'm just going to connect these here. Right? And so what I can see, and it helps if I draw it in, is that inverse functions are reflections of each other across the line y equals x. So here's that. And then here is the line y equals f inverse of x that I just found. So they are reflections of each other across the line y equals x. And then we can also see that every point has kind of a partner point on the other function. So let's say I look at this point here, which is 0, negative 2, and that point belongs to f. I have this point over here on f inverse, which is negative 2, 0. And I can see that they are just flipping that x and y, meaning they're just reversing the position. So they're switching spots. And then every point will have that on these functions. Okay, so let's let's keep going here. So what if a function is not one-to-one? Can it still have an inverse? Kind of. We say yes with some elbow grease. So let's consider the function g of x equals x squared minus 3, shown in this graph below. First, we'll ask, okay, is this function one-to-one? See how if I draw a horizontal line, it's hitting it at more than one place, and that only has to happen one time for it to get kind of thrown out. We say, not one-to-one. So this is definitely not one-to-one. And so the question is then asking, determine an interval on which g is one-to-one. So can I throw out part of a graph so then my function is one-to-one? So see how like over here on the left of the vertex and on the right of the vertex, I'm repeating y values, and that is not what I want. So what happens is I can actually just let's say I want to keep all of this part of the graph, which is from 0 on to the right, and throw out everything else. So let's say I want to like throw out this part. Okay. And so if they're asking me to determine an interval on which g is one-to-one, well, I found one. G is one-to-one if I restrict domain to starting at 0 and all the way to infinity. Now, why did I pick this? Well, I could have just picked everything to the left of 0, right? And that's just kind of dealer's choice. But what we like about picking this interval, right? Like I could have, what about the interval 0 to 1? And we go, well, then I don't get the whole range. So I don't want to pick something like that. I pick 0 to infinity because then I get the whole range. And so I'm not being cheated out of the range, even though I am limiting my domain. So what if I decided to do this? So then I say, well, now let's do the horizontal line test, right? So now if I do the horizontal line test, it's only hitting in one place, all right, at the most. So, and again, I'm imagining myself throwing out this other part. And so I'm only hitting the graph at one place with my horizontal lines. So then G is one-to-one if I restrict the domain. So that's a little bit of a kind of a hint of what's coming in terms of thinking about inverse functions, trigonometric inverse functions, and how we might be able to think about their inverses.